Hi everyone, today we are going to talk about ionic compounds and how they're made. So when we talk about ions, we're talking about neutral atoms that have lost or gained electrons. And it's always going to be the electrons. The protons are never going to change. If you think about the atom, the protons are in the middle and then the electrons are on the outside. It's the electrons that are being given and taken. It's never going to be the protons. So when we start talking about how there's a change in the charge, we're talking about changing the electrons themselves. With the cations are typically metals, and we're going to talk about that in this video, and they become positive because the electrons are being given away. Whereas the anions are typically nonmetals, and they're negative because they're gaining electrons. Remember, electrons are on -1 charge. And so if we're losing electrons, we're minusing a negative. So double negative means it's going to be a positive. So the cations end up being positive. Whereas the anions were gaining electrons, so we're gaining that negative charge. And so that's going to end up being negative. So when we're talking about the electrons that are given and taken, we're specifically talking about the valence electrons. These are the electrons that are on the outermost rings. So when we're talking about, let's say, sodium is atomic number 10, 1s2, 2s2, 2p6, 3s1. I'm sorry, it's atomic number 11. This last electron here with the 3, that's going to be the outermost electron. So if we have the 11 protons in the center, and then we have 1, 2, 3 energy levels, because that's the number 3 there, 3s1, so there's one single electron here on the outside. That single electron is the one that's going to be doing the reacting. That's the valence electron. So the electron that's on the outermost shell is the valence electron. That's the one that's going to be determining the reactivity. It's going to be the one that gain or lose electrons, and they're all trying to be like the noble gases. Again, we'll talk about this in this video more. The noble gases are on the far right, and they have a full octet. All of them are trying to be like that. So sodium's on this side. So it's going to lose an electron to come back and be like neon. So let's take a look at some of our electron configurations. Sodium is here. It's atomic number 11. So it's 1s2, 2s2, 2p6, 3s1. So you may be wondering how I got that. You should already know how to do this, but I want to double check with you. There's 7 rows. 1, 2, 3, 4, 5, 6, 7. And each one of those correlate to one of the periods on the periodic table. Now we fill in the orbitals. So we have S2, S2, 2p6, second energy level p orbitals, 6 electrons in there. 3s2, 3p6, 3d10 now, and so on and so forth. You should have learned this in the previous lesson. So this should not be anything new to you. Then for F14. Then once we get all of this done, we gotta draw those arrows that go diagonally. I'm only gonna do a couple more because you don't really need that many for this one. So rather than wasting the time. Okay, now I'm going to draw those arrows that go through it from the upper right to the lower left. And hopefully you remember that how we did this because we just took a test over it. Oxygen is here. It's the atomic number 8. So I'm going to count up these little numbers until they get to 8. 1s2, 2s2, 2p4. For beryllium, it's really easy. It only has 4. 1s2, 2s2. So when we're talking about the valence electrons, we're talking about the ones with the highest number. So 3 is the highest number of 1, 2, and 3. So those are the valence electrons. Oxygen, we have a 2 here and we have a 2 here, and we're going to combine those because they're both on the same ring. They're both on the same energy level. So there's actually 6 electrons here. And then with beryllium, we have 2 with it, 2s2. So you can actually predict how many valence electrons are in each row by just simply looking at it. You can count 1 to 8, and that will determine how many valence electrons are in each row. So for instance, beryllium, when we went back there and we looked at it, it has 2 electrons. Beryllium is right here. It's in the second row. That's how I know it has 2 valence electrons. Oxygen is right here, and we said it had 6. Right here, 2 and 4, 6. And it's in the 6th row. Sodium had 1. So there's a relationship between what row it's in and how many valence electrons there are. These numbers become very, very important. There's actually 2 sets of numbers we're going to end up writing on the tops, and that's one of them. So when we start looking at the electron dot structures, the dots represent those valence electrons we just pointed out. And the elemental symbol, so like Na, the symbol for Na, that represents everything else. It represents the core electrons, the electrons that are not valence electrons, and it represents the nucleus itself. So we said that sodium had 1 valence electron, so I'm going to put 1 dot here. If we were looking at oxygen, which had 6, 1, 2, 3, 4, you're going to spread them out like a box first, and then you're going to go back and pair it up, 5 and 6. So when we start looking at the blocks, and you had a video about this earlier, the S block is, and the P block are the representative elements. There are a total of 4 orbitals and a total of 8 electrons. So the first thing you need to do when you determine the electron dot structure is figure out how many valence electrons there are. And you do that by looking at what row it is. I'm not going to have you do the ones with representative elements, just the tall rows, just the representative. Draw the dots in an invisible square and then pair them up. So if I'm looking at nitrogen, I'm going to do 1, 2, 3, 4, 5, 6, 7, and 8. Those are our rows. If I'm looking at nitrogen, nitrogen is here. It's in the 5th row, so I'm going to put 5 dots around it. So I'm going to do it individually first. 1, 2, 3, 4. I usually go top, bottom, left, right, just to get them spread out. And then once I get to that point, I start pairing them up by just going clockwise. But remember, these don't have to stay there. They can move around. Electrons are constantly moving. So there's my 5th electron for nitrogen. Sulfur is here. It has 6 electrons. 1, 2, 3, 4, and then 2 more for 5 and 6. Beryllium is here. It has 2. So I'm just going to put top and bottom or left to right as long as they're spread out. And then boron is here. 1, 2, 3. But let's take a look at the 8th row. We have neon and we have argon. They're in the same row. They're in the same family. They're the noble gases. 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to do the same thing with argon. 1, 2, 3, 4, 5, 6, 7, 8. Both of them have 8 electrons around it. That is the maximum. 8 is the maximum for the representative elements. This is called the octet. Oct meaning 8. That means the s orbitals And the p orbitals are all full. Because you remember 1s2, 2s2, 2p6 stuff? Well, here's 2 and 6, and they can't put any more electrons in there. So it's actually really stable to have it completely full. So the octet rule is when atoms gain or lose electrons to mimic the noble gases. They want to be like those noble gases. So therefore, they're all going to try to get 8 electrons. To do this, metals tend to lose electrons, while nonmetals tend to gain them. That means the metals tend to be positive, while the nonmetals turn to be negative. Cation and anion come up quite often, so you want to make sure you know those words. So if I'm looking here, here's my stair step for the metalloids. If it's on this side, they're metals. If it's on this side, they're nonmetals. Which means this side is positive, while this side becomes negative. The transition metals here those are the D blocks. Those are where the D's end up, the D10s. You'll notice that there's 10 rows across here. That's because there's a row for each of the spots. Those tend to change. So as a result, we have to tell people what the charge is. Whereas if I'm looking over here, there's a standard set. So let's take a look at, wrong thing. We can actually determine the charges just by simply looking at the periodic table. If I'm looking at the periodic table, for instance, let's look at potassium. Potassium has 19 protons, 19 electrons. The nearest noble gas is 18. I could choose between 18 and 36. 18 is closer, so it wants to lose an electron. When it loses that electron, it becomes a +1. Magnesium here has 12, so you can choose between 10 or 18. Again, 10 would be easier, so it's going to end up losing electrons. So that's going to be a +2. You're going to want to write these numbers down because you need to have them memorized. Boron and aluminum. Aluminum here can choose between 10 and 18. 10 is closer, so it's going to be a +3. It'll lose 3 electrons. But then if we look at silicon can be 18 or 10, and it's in the middle. It's 14. So I skip that one, and I go to the next one. Phosphorus, it needs to gain 3 electrons. So to be like argon, so it's going to be a -3. Sulfur needs to gain 2. Chlorine and fluorine needs to gain 1. The halogens need to gain 1. And then the noble gases are actually stable. So that means that from this side, the metals have to lose electrons to be like the noble gases, while the nonmetals have to gain. And you want to keep these charges memorized because we're going to be using them a lot in this chapter. However, like I said, the transition metals have a tendency to change charges. There are some that stay constant, but manganese can be a manganese 2 or it can be a manganese 4. So you need a Roman numeral there to tell you what the charge is. So that scandium 2 means it's a 2+. It means it has a +2 charge. It gave up 2 electrons. The manganese 4 here, which is right here, is a +4 here, a 4+. That means it gave up 4 electrons to be stable. A couple that never change. You want to keep this in mind. You want to write this on your periodic table. Zinc is always a +2. Silver is always a +1. All right, so when we start talking about ionic compounds, I think I'm going to leave it here for now, and we'll do ionic compounds in the next video. Thank you.